attraction that all objects with mass have for each other. Like the electromagnetic force, gravity is effectively infinite range and obeys the inverse square law. At the atomic level, where masses are very small, the force of gravity is negligible. But for objects that have very large masses such as planets, stars, and galaxies, gravity is a predominant force, and it plays an important role in theories of the structure of the universe. Gravity is believed to be mediated by the graviton, although the graviton has yet to be isolated by experiments. Gravity is weaker than the strong force, the electromagnetic force, and the weak force. Mass is using computational force proportional to mass. This force is always effective. So, Earth is what takes. The gravity of the Earth has an acceleration rate of 9.78 meters per second squared.
The crumpled paper has less exposed surface area, so it heats less air as it falls. However, the flat paper heats lots of air, which slows its fall. For instance, we have feather coins. We will put them inside an evacuated tube. As you can see, the feathered coins fall at the same speed and with the same acceleration. So, air resistance affects the acceleration due to gravity of the two objects. If there is no air, the paper, whether it is crumpled or not, will fall with the book at the same speed and acceleration rate. Note that the weight or mass of an object has nothing to do with how fast things fall, only the air resistance.
It is the acceleration encountered to bodies by the attractive force of the Earth or an unelectric body. Acceleration is the change of velocity divided by the amount of time needed for the change to occur. It also takes place when an object speeds up, slows down, or changes direction. To calculate the acceleration of an object, we use the following equation. A is equal to delta V over delta T. In this equation, A is equal to acceleration, delta V is equal to change in velocity, and delta T is equal to change in time. If the acceleration of the object is the same for all time intervals, the acceleration that is said to be constant or uniform. Acceleration is measured in meters per second, or meters per second squared.
Other equations that are related to acceleration are velocity of an object with constant acceleration, displacement during constant acceleration, displacement when acceleration and time are known, and displacement when velocity and acceleration are known. Velocity of an object with constant acceleration, Vf is equal to Vi plus at. In this equation, Vf is equal to final velocity of the object, Vi is equal to initial velocity of the object, A is still the acceleration, and T is still the time. Displacement during constant acceleration, D is equal to 1/2 times the quantity of Vf plus Vi times time. The variables in this equation are the same as in the previous equation. Displacement when acceleration and time are known. D is equal to initial velocity times time plus 1/2 times acceleration times t squared. The above equation is composed of two terms. The first term, initial velocity times time, corresponds to the displacement of an object if it were moving with constant velocity, vi. The second term, 1/2 times acceleration times time squared, give the displacement of an object starting from the rest and moving with uniform acceleration. The sum of these two terms give displacement of an object that starts with an initial velocity and accelerates constantly. Displacement and velocity acceleration are known. Final velocity squared is equal to initial velocity squared plus 2 times a times d.
This type of acceleration is given a special symbol, g, which is the gravity. Since acceleration is a vector quantity, it has magnitude or size and direction. On the surface of the Earth, the freely falling object has the following acceleration. G for gravity is equal to negative 9.8 meters per second squared. Assuming there is no error systems, all equations given in this section can be modified to apply to falling objects by simply replacing A with G.